So hi, welcome back. So now that we have actually considered electronic stopping, we have a much bigger picture, a fuller picture of what happens every time pKa is generated. So just recap, you can see that the average energy of the pKa generated in an iron lattice is about 35 kilo electron volts. In actual fact, slightly less. And of course, depending on the scattering angle, the pKa energy will change. So remember our two extreme cases between 180 and 0 degrees. At the 0 degrees scattering angle, there's actually no scattering actually occurring. At 180, you have energy about 68 to about 70 kilo electron volts being transferred to the pKa. So if the neutron is knocked back 180 degrees, we will have to consider some degree of electronic stopping. And we note that, the neutron the pKa can transfer its energy to other atoms via electronic stopping, or it can collide into another atom, thus causing another displacement to happen. So if T is more than EC, where EC is the threshold for electronic stopping to occur, we can have two effects happening. One is the collision, and the other is that it will just ionize. You'll just ionize the atoms along the way, and thereby lose its energy. However, how do we consider how to calculate the displacement per atom for this regime? Now, the simple thing is, we'll just have a very simplified assumption. We'll just consider that when T is more than EC, only this electronic stopping effect occurs. So we have pKa's with energy more than the electronic stopping threshold, which was about 56 kilo electron volts, around that range. We actually see that the number of collisions produced, we can see that Vt equals to EC over 2 ED. Okay. How do we calculate this? This is the number of vacancies produced or displacement produced. Now, we could derive this, from our previous examples. If you remember this from many videos ago, we've calculated how many displacements we can have. So, we actually plugged in some numbers, but we didn't actually calculate some expression, a general expression for this to occur. Now, how do we derive this? Okay. How do we derive this? We actually can see, remember that NF equals to ln T over T of pKa over ln of half. That's the number of generations that occurs. So if you want to calculate the number of displacements, we have 2 to the power of NF. So that's the V of T. 2 to the power of NF. Okay. Alright, so how are we going to do that? 2 to the power of ln T over T of pKa okay. And this we have talked about before from several videos back. to be about 35 kilo electron volt, and this we call the energy threshold, 2ED being the energy threshold. Okay, that was from several videos back. I'm sorry for the disjoint. If you need some refreshers, please can review that video and come back. Okay, that was derived over here. Okay, so now that we have this, all right, we will have to do some mathematical somersaults, all right, to get this into some form of a simpler expression. Because to the power of ln something, that just looks ugly. Okay, so what can we do? First thing, we might want to change the base of this logarithm. Alright, let's change the base of this logarithm to the base of 2. Alright, so let's do that. And why are we doing that? Let's say you have e to the power of ln x, and that was, what is that equal to? Or 2 to the power, e to the power of ln x. So we have a log base e to the x equals log base e to the x. This is some simple mathematical trick, and we take the exponent of both sides. So we take the exponent of both sides, or rather we ln x equals to ln x. So we know that from the definition of the logarithm, x equals to e to the power of, we take this, take the power of e to here, and we have this expression, x equals to e to the power of ln x. That's from basic logarithms. Now, we can generalize that to mean that if it's a base of 2, x equals to 2 to the power of log 2x. Okay, so all we need to do in this case here, now we need to change the base of this logarithm to base 2. So that's what I'm going to do first. Okay, so what am I going to do first? I'm going to do this. I'm going to change the base. So I'm just going to copy this expression to the next page. 2 to the ln t of pKa times ln of 2. So why am I doing that? Okay, I think I better not do that. Maybe a careless mistake. Let's take it one at a time. Ln of half. Alright. So ln of t over t of pKa over ln of half. So how do you change base? Let's say you have a log of a of b, and you're going to change it to base 10. So this is the change of base formula. And just get it from a Wolfram or something. Let's double check. Okay, so that's you can just Google that and you find that out. So let's change the base of this top one. And of course, let's change the base of the bottom as well. Alright, that's all I was doing. So I'm going to change the base of this by doing this. And now, what's next? Next thing is to combine these into one equation. So let's do this. Ln T over T pKa, ln of half. Okay, so I have this divided by this, and this 2 log base 2 of E, that will cancel out. So we'll be left with this expression. And what do we notice? This log 2 half, well, half is equals to 2 to the power of -1, right? So the logarithm of such is just -1. This is equals to minus log base 2 T over T of the pKa. Now I can just change it to this. Alright, so now it's way more simple. Let's put it back into, let's plug it back here, because now we have a very simple expression. So 2 to the power of log 2 T pKa over T. Alright, T equals to 2ED here, because that's the threshold energy. So this T is the T of the energy of the initial pKa. So all this will just truncate to this. Alright, so V, the number of displacements or number of vacancies, excuse me, number of vacancies or displacements, I'm just going to use the nomenclature V, based on the energy of the incoming pKa, that is equals to T of the pKa over 2ED. Now, if you were to consider that T pKa more than EC, as is the case of electronic stopping, what will happen? We will consider that at E more than the energy of the pKa more than this electronic stopping threshold, there's no more electronic stopping that occurs. That was our assumption. So V T pKa more than EC, alright, V where TKA is T of the pKa, the kinetic energy of the primary knock-on atom, more than the threshold, electronic stopping threshold, that will simply be equals to EC over 2ED. Now we have derived that. So this is based on the simplifying assumption that when our pK energy being more than this electronic stopping potential, there is no pKa being generated. Everything just it just loses energy via ionization. Okay, so at slightly less than this value, if T pKa equal to EC, then V, if the T pKa is just equals to EC, that will also be EC over 2ED. That's how many displacements are made per pKa. So at slightly lower than this, what will be the characteristic formula? We'll just use this. Okay, we'll just use this formula. All right. So you can see there are already two regimes. So T pKa more than EC, V T Okay, EC equals to ED. TPKA less than EC. VT equals to TPKA to ED. Alright, so these are two of the regimes. How about when T is less than T of a pKa less than ED? ET equals 0. Why? If the energy of the pKa is less than the displacement energy, you cannot displace any atom. How about Tpka less than 2 ED? Excuse me. Vt equals to 0 also. Oh no, it doesn't equal to 0. It equals to 1. So these are important threshold energies. So at Tpka equals 2 ED, usually there's one more knock-on atom being made because the energy is just enough to displace one more atom. So at Tpka less than the ED, no displacements. Tpka less than 2 ED, but more than ED, you have one atom displaced. Any more than that, you will have this regime happening. Alright, you have this regime happening. Tpka, Vt equals to Tpka over 2 ED. So, can we put this together into a diagram? Absolutely, and that will help us to see what's going on. So this is the number of vacancies or the number of displacements that are occurring. So let's draw this. Remember at Tpka less than ED, there are no vacancies being produced, so this is 0. Between 2ED and ED, that's one displacement happening. So these are the important points we must note. And in this energy range, 2ED to EC, you can see that there's a linear relationship between Vt and Tpka. So I'm just going to draw a straight line up. Okay, until a certain threshold, EC, where after that, so this is EC, for irons about 56 kilo electron volt, or slightly less than that actually, so there's an approximation. So we have this number of pKs being generated. So let's look at a diagram where you have the vacancies produced, or how many displacement being produced per pKa. Okay, so at maximum we have this EC over 2 ED. Alright, so that's 56 kilo electron volt over 2 times 35. Okay, 56,000 divided 2 divided by 35. So EC for steels, that can be about 56,000 EV. So EC over 2 ED, that will be equal to 56,000 over 2 times 35, and that will be about 800 vacancy per pKa. Okay, any more than this, the simplifying assumption of course is that there are no more pKa's being generated. Now this model has a name. It's known as the kinchin-pease model. Kinchin-pease model. It's being made by, I think, these two guys. So yeah, they considered the assumption that in this regime there's hardly any pKs being generated, so they just ignore that proportion, that component. Over here there's a very much a cascade that's being made. The two body elastic collisions as being described earlier, we calculated using the lambda, and so this is the cutoff energy that we need to take note. We've already derived that when we discussed electronic stopping. So yeah, the energy transfer cross-section is also given by a hard sphere model, and the arrangement of the for this kinchin-pease model we have to neglect the arrangement of the atoms in the solid. So back a few videos ago when we are discussing cross-section, okay, we consider this lattice of ions or atoms. So we know that it's like this, a nucleus surrounded by an electron cloud. So sometimes if the pKa, we have this pKa coming through here, if it's going to go through this section of the lattice, the probability for collision is way higher than the pKa traveling through this. But for our cross-section analysis, we didn't encounter this, or we didn't factor this into account, because we just assume a homogeneous lattice where this effect does not occur, and this is known as channeling. Okay, so we ignore channeling for this kinchin-pease model. We ignore channeling. Okay, so we don't think of the effects of the crystal structure. But for a guesstimation kind of thing, this is a good enough thing. If you really want to consider all this channeling and everything, we might need to use some simulation programs that use a Monte Carlo code. Okay, and in class I learned, I think they call it SHRIM, which is the stopping range of ions in matter. So just to let you know, such programs do exist to really help us to calculate dPA. And as a final note, we should note that this kinchin-pease actually describes pKa's. They don't describe the neutron itself, but the pKa is the neutron. The neutrons generate as they fly through the lattice. And why? How do we know that it's not a neutron? Well, if it was a neutron, there will be no electronic stopping we have to consider. So that's something for you to remember. So now we have enough information to describe how many displacements are produced by a pKa spectrum produced by each neutron. Now this is just half the picture of the neutron damage and how we quantify it. Because, cross-sections are pretty complex things. So we'll discuss more about that in next video, where we talk about neutron spectra and trying to find a displacement cross-section. Okay, so thanks for watching. I'll see you guys in the next video. Bye bye.